Okay, so the takeaways from the notes. Well, there were no notes. That's right, forgot about that. Night off. So no takeaways. Yay. Let's just take a little word wall break. So our word wall is pretty super tiny. Because I only have our 3 cards up there so far. And believe it or not, I start them up there because by the time we get done with everything, we're way down there at the bottom corner of the bulletin. So we'll fill it up. Okay, so what do we have here? We have the definition of a limit, right? So looking at that card, remember the definition of a limit gives us a language, right? Math is a language. Gives us a language that explains where the y values are trending, where the outputs are trending, right? As the inputs approach a certain value. So the outputs, I think, are that blue things. The inputs are the green things on that card. Okay, so where are those outputs trending as we approach a certain input? Hi. Okay, give me a few seconds or a minute or two. The definition of a limit. So we got that. So on the next card, sine x over x, right? It's this thing, right? Okay. So we know that sine x over x is 1. So let's extend this a little bit. Anybody want to venture what sine 5x over 5x is? Also 1. For reasons that you don't really know yet, and not for the reason you might think. Why do you think it's 1? Five divided by 5 is 1. That's for the ratio heights. Like if this was sine 3x over 5x, it'd be 3/5. Okay. Now, does that mean the 5s are canceling? No. Yeah, exactly. Right. The 5x inside the sine function can't cancel with the 5 in the denominator. So it's not for that reason, but that limit is a ratio of those 2 numbers. That's what the limit will always be, and for reasons that we will get into during Unit 4. Okay, we just don't have what it takes right now to address those. Sine of 5x over x. Anyone want to venture a guess? It's 5, exactly, right? We have an imbalance in the numerator. Sine of x over 5x. 1/5. Yep. Okay, so it's still a ratio of those 2 coefficients in front of the x. Okay, and we'll get more comfortable with that as time goes on. Okay, and then the last card on the word wall is the squeeze theorem. Okay, so look at that. The picture is powerful. Okay, everything's got to squeeze together at that point we're evaluating the limit at. That's the only way we can determine the limit, is everything comes to the same value. Can't have any gaps. Okay, so any questions about that? All right. So, oh, I forgot about that. Okay, so today we have not quite sure why that picture is. Oh, I know why. Okay, a little bit about con. I think we're all kind of getting the idea here. 100 is the A in the grade book. 75 is a B in the grade book. If it's somewhere in between, then I give you an AB. If it's closer to 75, I give you a B. If it's closer to 100, I give you an A. If we have lots of con. So our essential question for today was, what is continuity, and when do we have it, and when do we not have it? Okay, and so it's kind of an involved essential question, right? There's 3 of them really. So take a second, write down that essential question in your notes. We have an activity to do in your notes. I just want to go to the next slide here. Oh, good. Oh, that's I'm not quite sure why that says that. Oh, I know why. Okay. Yeah, go ahead and get down that essential question. And while you're doing that, I am going to talk to this student. Okay. So we're going to do a little taking sides activity. So right now, we're going to stand up. We're going to get ready to move. This is have my center aisle here, right? And so I'm going to take these sides and then take this side. All right, so you can hang out there for a second just to kind of get the question here. So how many numbers are there between 1 and 7 inclusive? Okay, that's the answer. So how many, if you think it's 7, go to that side. If you don't think it's 7, tell me this side. And the fact that I'm standing over here means nothing. I'm just by my computer. So don't take my position as anything. By inclusive, I mean start at 1, end at 7. Okay. So the hallway side is 7, and the non-hallway side is not 7. And you can't stand in the middle. And you have to stand. Okay. Next question. The basic colors of visible light are red, orange, yellow, green, blue, indigo, violet. How many is that? 7. How many people believe that visible light spectrum contains 7 colors? Stand over here. How many people believe it doesn't contain 7? Stand over there. Okay, so we know what your answers are. What's your answer over here? Because not 7 is a lot of other answers. I can't. Oh, infinite. Okay, anybody else have any other answers? Anybody want to change your answer? Infinite's a lot of numbers. Does everyone else think it's the same as infinite? Anybody want to change your answers? I'm thinking infinity is too much to deal with. I want to go down over the side. You guys have 7?
No.
Okay. So, okay, what are the numbers between 1 and 7 inclusive? Okay. Those things, right? On the number line? Oh, I'm wrong. What is this number? How many numbers do you have now? 5. Oh, well, this 8. All right, so you want to stay in the 7 world? It's not easy being alone. So, you might say 7's the nice world. So with 7 around, we need more than 7 numbers now. So we still stuck on this infinite thing? Yeah, still stuck on this. So why?
Because you can mix with colors, it's different from numbers, but you can mix colors, get different colors.
Sure.
With numbers, you can go into full numbers and you get that fraction.
Right? What do you call that? No gaps, no holes. You always keep going in between. So we call the numbers in the number system real number line. Visible spectrum is a continuous spectrum. We must have gone. All right. So we know now that we really have a continuous scenario for each one of those two There's the visible spectrum, right? There's no gaps or holes in the visible spectrum. And so so we have some notes before the activity here, kind of doing the notes in class. I guess I could have done this, you know, in the videos, but it seems funner to have you move around. Okay, so here's our definition of continuity at a point. Okay, interior points. Notice it's breaking it up. Okay, so we're kind of learning how to read the book here. We interior points, the stuff on the inside, and then we have the endpoints, right? The beginning and the end. So the interior points, a function, y equals f of x is continuous at an interior point of its domain if wherever we want to pick, our limit and our function value are the same. Does that make sense? So in other words, if we go back to our function we had on the first day, if I look at this part of the domain, every limit and every function value are the same. Does that make sense? If I would look right here between 2 and 5, that's not true. Does that make sense? And at 3, the limit is different than the function value. So it would not be continuous in the domain from 2 to 5. In fact, we know it's not continuous. It's got a hole, it's got a gap. Okay, now the reason why we talk about the endpoints differently is because we know limits are two-sided, but if we're at an endpoint, like here, okay, limit exists, function exists. If we're at an endpoint, here A or here B, then we're looking at a one-sided limit. Okay, so when we look at this, we say, well, we have a left endpoint, which is A, and so this limit as we are approaching A from the plus side has to equal the function value. And then at B, the limit as we are approaching B from the minus, the smaller values, has to be equal to the function value at the endpoints. So that's their continuity at the endpoints. We deal with one-sided limits. Continuity on the interior, we deal with two-sided limits. You doing okay? Okay. So look at that dot. Are we continuous from A to B? Do we have a situation where if we travel from A to B, we're going to hit everything between A and B? So we have continuity. Does that make sense? Okay. So you have 2 minutes. I want you to go to page 76 in your text. Get the 4 examples of discontinuity. There are 4. Okay. I know you've got space for 5, but we lump B and C together as one. Okay. And go ahead and diagram that into your notes, please. Okay. There's an even. If you don't want to use it, it's on about page 76. Oh, anybody else want to? It's about page 76. Anybody else? I'm just not quite sure exactly where it is. This is just an older version. It's heavy too. 76. Yeah, roughly. Oh, okay, yeah, that one. It should be in the text. It should be. I don't know. Is it on page 76? textbook. One eighteen. The people I loaned books out to, we don't have this in this book. Yeah, well, it's not our textbook. It was just a different textbook. So you have to use the e-version. Oh, calculus second edition. Yep, in the left sidebar, calculus second edition. So it says calculus second. Okay. Okay, so here it goes into notes. You have continuity. And so you have a box at the bottom of that page. We're going to call it friendlier verbiage for continuity. Looks good. Looks good. Yep, I agree. Okay. So I see people are pretty far along. So let me just kind of put those pictures up there for you. So that's why this is why we lump B and C together. And I know yours is top and bottom, but this just fit better on my screen. B and C we lump together because they both have holes. They both have this scenario that we did on the board at x equals 3. Okay, so notice we also have a stray value up here on this one that we don't on this one. So the idea is we can fill a hole. If we've got something that is just a gap at a single location, we can fill that by canceling those factors in the numerator and the denominator when we factor rational expressions. Right? We cancel those factors, that cancels the whole. And so those are really common because every time you get a whole, it means that you factored something and canceled it, you got the bottom. Okay. The next one, figure D, is a jump discontinuity. Okay. So we're jumping in value instantaneously from 0 to 1. Okay, and we can only be at one of those values. In this picture, they chose to be at value 1. Okay, you see that with piecewise functions all the time. Okay, they jump like that. Figure E is where we start to have asymptotes, vertical asymptotes. What has to happen in a rational expression, a fraction, to have a vertical asymptote? Something over 0, right? It's when the denominator equals 0. So that rational expression, notice when we put 0 in for x, it's 1 over 0. Okay, for this totally made up function, this is -2. We don't know what the function is here already, but somehow in the denominator we have x plus 2. So that we have a vertical asymptote at -2, right? Because that's what will make it 0. Okay. And so we have that x plus 2 factor down there, and we can't cancel it. Okay, so that's how we get our vertical asymptotes. And then oscillations are very, very rare. So the oscillations, sometimes we have, if you notice, this oscillation has a horizontal jump. Like there's nothing in between here that has any actual values. Okay. And they're rare. But the other three you'll see all the time. So questions about that. So those are the 4 discontinuities: removable, jump, infinite, and oscillating. Okay. So if you don't have one of those 4 things, then you must have continuity. So let's talk about some friendlier versions of the definition of continuity. What do you have to do to get past the location of discontinuity? So think about it. Here I am, I'm drawing my function, I come up to the discontinuity. What do I have to do to continue? I can't. What do I have to do with my pencil? Lift it up, come over here, and then what? I can keep going, right? Let's take a look at, ooh. There we go. Let's take a look at this one. I'm on the function, I'm gonna come up to here, what do I have to do? Lift up my pencil, right? And go up there. How about here? Do I have to do the same thing? Right, come up here, I gotta lift up my pencil. The same thing with the oscillating. Lefty. I oscillate, I get to this point, I gotta lift up my pencil, come over here and continue. Right? So if that's the case, just got done drawing these. What did you have to do to get past the location of discontinuity? I had to do what with my pencil? Lift it up. So if that's the case, if I lift my pencils on discontinuities, what am I not doing when it's continuous? I'm not lifting up my pencil. There's your friendlier verbiage. The function is continuous at an x location, at any x location, if you don't have to lift your pencil or draw it. So that function is continuous from A all the way to B. It's continuous at A because the limit function values are the same. It's continuous at B for the same reason. And at least that gives you a visual, a kinesthetic definition that hopefully you'll remember. I'm drawing this function. I don't have to lift my pencil. I must have a continuous. Okay? Okay. Just give me a little bit of wait time here. Okay, so that's the friendlier version. And with that friendlier version, we are going to go into our 3rd resource. Okay, and I call this a foldable. So we have this. Fold it. More or less. And then this one, you're going to pull up. And you're going to make sure a black dot. Got a black dot. See, that is So, not here. Not because I have a box button here. Because I have a box button. So, what you are tasked with, and just looking at, there's a definition, just kind of looking at the time, I think what I'm going to do is redesign the topic questions, get rid of today's topic questions, put them on Monday. Okay, so I'm going to do a bit of a read on this. So we're just going to do this, look on this, and look on time. Okay. Okay, so we've got this folded. And so we're looking at the definition. And so you are going to work through this foldable. You're going to look at the inside and see the top. It says explain in words why the graph to the left. So explain in words why the graph to the left is not continuous at the indicated point, right? -1 in this case. Explain why. What is there? There's discontinuity there. You have to tell me. Okay? So that's the first task. The next task, okay, we're going to go in and complete the next tasks. And the next task is actually you picking out the appropriate graph that fits the description and taking it in, and then you sketching another version of what you take. You're not going to use all of it. Okay? So let's go ahead and get another buddy or a hotmate or a friend and work through this. And then after you work through this, whoops, I got my order wrong. After you work through this, don't worry about the topic questions, just start on the time, okay?